Om Namah Shivaya. Good evening to one and all present here. On behalf of Department of Electronics and Communication Engineering, Internal Quality Assurance Cell and Institution Innovation Cell of Sri Sathyam College of Engineering and Technology, I extend a warm and heartfelt welcome to the ATAL online 6-day faculty development program on semiconductors for smart systems, applications in IoT, artificial intelligence, and next generation devices, sponsored by AICTE and scheduled from 6th to 11th October 2025. We are truly privileged to have our respected chairman, founder and principal, heads of various departments, faculty members, colleagues, and enthusiastic participants with us today. Let us begin this auspicious inaugural function with the invocation. I kindly request everyone to rise for the Tamil Thai Valthu.
நீராறும் கடலுடுத்த நிலமடந்தை கெழிலொழுகும் சீராறும் மதனமென திகழ்வரத கண்டமிதில் எக்கணமும் அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே உன் சீரிழமை திறம்பியந்து செயல் மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே.
Thank you. Please be seated. To formally welcome the gathering, I now take the opportunity to deliver the welcome address. Om Namah Shivaya. A very pleasant and warm evening to everyone present here. It gives me immense pleasure to welcome you all to the inaugural function of the AICTE ATAL online 6-day faculty development program on semiconductors for smart systems, applications in IoT, AI, and next generation devices, organized by the Department of ECE, Sri Sathyam College of Engineering and Technology, in association with Internal Quality Assurance Cell and Institution Innovation Cell from 6th to 11th October 2025. At the outset, I extend my heartfelt welcome to our beloved chairman, Dr. V. Balakrishnan sir, whose inspiring leadership constantly motivates us to aim higher in all our academic and research endeavors. On behalf of organizing committee, I welcome you, sir. I extend a warm welcome to our respected and beloved founder and principal, Madam Dr. V. Sujatha, for her continuous encouragement and support in all our department activities. On behalf of organizing committee, I welcome you, ma'am. I also extend a cordial welcome to all the heads of the departments, their faculty members and non-teaching staff who are with us today, contributing to the success of the program. A special word of welcome to our eminent resource persons, Dr. Jnana Jabadas, Professor, Villa College of Maldives, QA Campus, and Dr. Neeraj Kumar Mishra, Associate Professor, Vellore Institute of Technology, Andhra Pradesh University, for graciously accepting our invitation to deliver expert sessions and share their rich knowledge and experience with us. On behalf of the organizing committee, I welcome them, both of us. The theme of the FDP is timely and significant, focusing on the rapidly evolving the field of semiconductor, which forms the backbone of the next generation intelligent systems. This program aims to provide participants with deep insights into device level innovations, materials, and semiconductor technologies that power Internet of Things, AI, and advanced electronic systems. We are delighted to have enthusiastic participation from faculty members and researchers across various institutions in India, and I am confident that the sessions planned over the next 6 days will enrich our knowledge, inspire the collaborative research, and spark new ideas for innovation. On behalf of the Department of ECE and the organizing committee, I once again extend a warm and cordial welcome to each and every one of you to this inaugural function and the exciting academic journey that follows. Thank you all and wishing the FTP a grand success. Thank you for giving me this opportunity. Next, we are greatly honored to have with us our beloved founder and principal, Madam Dr. V. Sujatha. I kindly request Madam to deliver the felicitation address.
Warm welcome and pleasant evening to one and all present here. Honorable Chairman, Dr. V. Balakrishnan, Sri Sathyam Group of Institutions, most respected resource persons of today's program, Dr. D. Jnana Jabadas, Professor, Faculty of Engineering and Technology, Birla College, Maldives, Dr. Neeraj Kumar Misra, Associate Professor, Vellore Institute of Technology, AP University, India, and all other experts from various organizations. Respected Professor Dr. Kannan, HOD of ECE, Sri Sathyam College of Engineering and Technology, Sangagiri, and the co-coordinator of this faculty development program. Respected participants from various organizations all over India, dear teaching and non-teaching faculty members, heads of various departments of Sri Satyam College of Engineering and Technology, Sangagiri. It's indeed a great honor and privilege for me to deliver the felicitation address before you on this special occasion of the ATAL Faculty Development Program on Semiconductors for Smart Systems, applications in IoT, AI, and next generation devices. The duty which is conferred upon me is to deliver the felicitation address. Before going to start my address, it's my pleasure to take this opportunity to extend my heartfelt gratitude to our chairman, sir, Dr. V. Balakrishnan, Sri Satyam Group of Institutions, for his unwavering guidance and support to make this event possible. Thank you, sir. My sincere thanks to AICTE and ATAL team for selecting our institute and for providing fund to conduct this wonderful faculty development program for the betterment of academicians, researchers, and also the institute. I would also like to take this opportunity to felicitate and thank the eminent speakers and experts from various organizations who have graciously accepted our invitation to share their insights and knowledge in spite of their intensive schedule. Thank you, sirs and madam. Your expertise will surely inspire our participants and open new avenues for teaching, research, and innovations. I would also like to congratulate the organizing committee and the co-coordinator, Professor Dr. Kannan, for their tireless efforts in bringing together such a meaningful academic event. My special thanks to Professor Dr. Chitra, Madam, for her initiative and the support towards this faculty development program. She is the academic advisor of our institute. Thank you, Madam. And my best wishes go to all the participants and their institute for their active participation. Without your presence, this function will not be a successful one. So thank you all the participants. Coming to my address, our topic is Semiconductors for Smart System, Application in IoT, AI, and Next Generation Devices. Dear participants, we are living in an era where semiconductors form the backbone of modern technology. From the smartphone in our pockets to the autonomous vehicle on the road, from life-saving health care devices to smart cities. So semiconductors are not just a component of a system, they are the very useful enablers of innovation and progress. Today, with the integration of the Internet of Things, artificial intelligence, and potential of smart systems is expanding beyond our imaginations. These technologies are shaping a world that is not only more efficient, but also more intelligent, interconnected, and sustainable. This faculty development program under the visionary initiative of the AICTE ATAL Training and Learning Academy is therefore both timely and significant. It provides a platform for our faculty members and researchers to gain cutting-edge knowledges in semiconductor technology, artificial intelligence, and their applications in emerging areas. Such program ensure that the academic community is not just a spectator, but an active contributor to India's journey towards becoming a global hub in electronics, design, and advanced technology. The future of semiconductor in India is not just a technology, it's about empowerment. It will create more employment, strengthen our national security, and make India a driving force in the global digital economy. May this FDP ignite new ideas, foster collaboration, and provide the way for next generation devices and smart solutions that serve the larger society. Let us prepare ourselves to contribute to this transformative journey. As the coordinator of this FDP, I would like to share some important information about this 6 days online FDP program. The duration is 6 days. Today is the first day and 11th will be the last day. Each day we will have two sessions and two experts will address each and every day on the relevant topic. The session starts from 6 p.m. to 9 p.m. And each session length is 90 minutes. Last day, on the final day, on 11th, you will have to attend an online test and you should score minimum 70% of assessment mark. Along with that, you have to score 80% of attendance. So those who meet these two conditions will receive their certificates in digital format. So these are all the basic things. I hope you would have already received all the informations, and I encourage you to attend all the sessions without fail and to make use of this valuable opportunity. My best wishes to you all. Once again, I extend my warm felicitation to everyone associated with this program. Let us continue to learn, share, and innovate for a better tomorrow. Thank you, one and all. Thank you for the opportunity given to me. Thank you.
Thank you, madam, for your kind and motivating felicitation. It is our privilege to invite our respected chairman, Shree Sathyam Group of Institution, Dr. V. Balakrishnan, sir, to deliver the presidential address.
Very good evening to everyone, sir.
Good evening, sir.
It gives me an immense pleasure to be the part of the inaugural function of this AICTE sponsored ATAL online faculty development program on semiconductor for smart system applications in IoT, AI, and next generation devices. At the outset, I wish to extend my hearty congratulations to the Department of ECE, the IQAC, and the Institution's Innovation Council of Sri Sathyam College of Engineering and Technology for the successful organizing this FDP under the ATAL Academy initiative of AICTE. I am delighted to note that this program has drawn an overwhelming response with 193 participants from various institutions across India. Registering for the FDP, this reflects the keen interest and enthusiasm among the faculty members and researchers to enhance their knowledge in the ever-evolving field of semiconductor and smart systems. Semiconductors are truly at the heart of today's digital revolution, powering devices, systems, and technologies that define modern life. The integration of IoT, artificial intelligence, and advanced semiconductor innovations is transforming every sector from healthcare to smart infrastructure. I am glad that our institution is contributing to this transformation through such a meaningful academic platform. I take this opportunity to appreciate our founder and principal, Dr. V. Sujatha Madam, for her continuous encouragement and guidance in promoting equality in the quality faculty development initiatives. It is also commend Dr. B. Kannan HOD, ECE, and his entire team for the dedicated effort in planning and coordinating this FDP. So all the resources person and participants joining from different part of the country, I extend a warm welcome. I am confident that this FDP will provide an enriching learning experience, fostering collaboration and innovation among the academicians and researchers throughout India. Let this program serve as a catalyst to inspire new ideas, empower our faculty community, and strengthen the vision of building a technologically advanced and self-reliant India. I once again congratulate the organizing team and wish the FDP great success. Thank you, one and all, and best wishes for the fruitful and inspiring week ahead. Thank you, sir. Thank you. Please go ahead.
Thank you, sir, for your inspiring presidential address and continuous encouragement. I now invite Dr. S. Magendran, sir, HOD of Electrical and Electronics Engineering Department, to propose the vote of thanks for the inaugural function.
Respected dignitaries, esteemed speakers, faculty members, and dear participants, a very good evening to one and all gathered here. It is indeed my privilege and pleasure to propose the vote of thanks on behalf of the Department of ECE, IQAC, and IIC of Shree Sathyam College of Engineering and Technology, Sangagiri, Salem District, for the inaugural function of our AICTE sponsored ATAL online FDP program on the title of Semiconductors for Smart Systems Applications in IoT, AI, and Next Gen Devices. First and foremost, I extend my heartfelt gratitude to our Honorable Chairman Sir for his inspiring presidential address and for his constant encouragement and visionary leadership that continues to guide us in all our academic endeavors. Thank you, sir. My sincere thanks to our beloved founder and principal madam for her felicitation address and for being a constant source of motivation and support in organizing this kind of FDPs in our campus. Thank you, ma'am. I express my deep appreciation to Dr. P. Kannan sir, HOD of ECE Department, for the welcome address and for his tireless efforts to make this function a live one as the coordinator in planning and executing this FDP. A special word of gratitude to all the head of the departments of SSCET, faculty members of SSCET, and participants from various institutions for joining us in this academic celebration of innovation and learning. Thank you all. We also extend our sincere thanks to AICTE for sponsoring this FDP under the ATAL Academy, thereby providing a valuable platform for knowledge exchange in emerging technologies. Last but not least, heartfelt thanks to all the members of the organizing committee, the technical support team, and the student volunteers for their dedicated contributions that made this inaugural event a grand success. Once again, thank you all for your gracious presence and support. I also look forward to your active participation in the upcoming technical sessions that follow. Thank you very much for the given opportunity. Thank you. Jai Hind.
So thank you, sir, for your thoughtful words of gratitude. Now I kindly request everyone to rise for the national anthem.
जन गण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंधु गुजरात मराठा द्राविड़ उत्कल गंगा विंध्य हिमाचल यमुना गंगा उत्कल जलधि तरंगा तब शुभ नामे जागे तब तब शुभ आशीष मांगे, गाहे तब जय गाथा। जन गण मंगल दायक जय हे भारत भाग्य विधाता। जय हे जय हे जय हे जय 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 हे।
With this, the inaugural function comes to a close. We now proceed to the technical section of day 1. Dear participants, the technical session will start at sharply 6:30 p.m. I request all the participants to stay on the line. The technical session will start at sharply 6:30 p.m.
Topic semiconductors for smart systems, applications in IoT, AI, and next-gen devices. Actually, the introductory part I'm just going to present, and it will be briefly concentrating on the introductions part of how semiconductors been utilized for the modern day smart systems and all. In the presentation overview, it goes like the basic of semiconductors and followed by the CMOS technology and microelectromechanical systems, as well as the system on chip, and finally with the FinFET. So these are all the basics which actually contributes to the modern day smart systems. When we talk about the semiconductors, semiconductors are materials whose electrical conductivities are higher than those of insulators, but lower than those of the conductors. So it is not actually a conductor, but it is not actually an inductor too, but it will be actually conducting when the temperature increases. When the temperature increases, the resistivity decreases, and based on that, it will be conducting. So silicon, germanium, gallium arsenide, indium, antimonide, and cadmium sulfide are some commonly used semiconducting materials. And basically, we have some introductions related to the silicon as well as germanium that will be much useful in the wafer processing as well as the other processes which are being included with VLSI design, the VLSI technology, CMOS technology. And semiconductors have negative temperature coefficients of resistance. As the temperature increases, the resistivity decreases. So, and the second thing is we just have to have a comparison over the energy band gap of the insulator, semiconductor, as well as the conductor. So the first diagram actually shows the band gap between the valence band and the conduction band. So when the energy is being applied to the valence electrons, these valence electrons will be just getting the energies and easily that can skip to the conduction band. So when you compare or when you just see the insulating material, so the energy or the binding and force between the valence electrons as well as the nucleus, that is higher here. So the band gap between the conduction band and the valence band, it is much higher, larger. So there is no chance of just escaping from the valence band to the conduction band. So this conduction is actually almost impossible in case of this insulator. So when you just move ahead with this semiconductor, the valence band and conduction band, the energy band gap, it's actually a very much minimum when it's compared to the insulating material. So because of that, when the valence electrons gains much energy, it will just easily skip to the conduction band, and thus the conduction will happen in a controlled manner in case of semiconductor. So when it is in as a conductor, so the valence band overlaps with the conduction band so that conduction can be easily occurred in case of the conductors. So when you just try to classify the semiconductors can be classified as the intrinsic or the purest form of the semiconductor and extrinsic. Extrinsic means we have to add the impurities in order to change its conduction characteristics. So by using some doping methods, or the doping is the process of adding the impurities into the semiconductors. By using some doping methods, we can add the N-type or P-type semiconductor or the impurities into this semiconducting materials. So generally we will be using a pentavalent impurity, that's the valency 5. So it will readily combine with the silicon atoms in the lattice structure to just meet the or to complete the valence shell. And one electron, the excessive one electron, will be left as a free electron. And in case of a trivalent impurity, it will already combine with the 4 valence electrons of the silicon, and the valence band needs another 1 more electron, so it will be electron greedy. So we can say that the existence of holes which is available with the trivalent impurity can be readily formed, and that will create a p-type material. So this is the basic structure, extrinsic semiconductors. And we will be dealing with this extrinsic semiconductor because we will be adding the extrinsic semiconductors in the form of doping, or through the process of doping or ion implantation processes. So here we can see the pentavalent atoms. So that will actually have a donor impurity contributes a free electron because it is already settled with this silicon lattice structure when it is replacing a silicon existing atom. So the valence shell, it is actually having 8 electrons, and it is more stable by leaving or by donating 1 free electron. So this will create the electronic charge or the negatively charged particles to just the concentration of negatively charged particle inside that lattice structure will be maximum, and that will create a N-type material. So it can be lightly doped or a moderately doped or a heavily doped based on the requirements. For example, if you are creating a source or the drain regions of a transistor, we will be preferring the heavily doped conditions. And if you are justly preferring for a substrate or epitaxial layer, we will be going for a lightly or a moderately type doping profile. And in p-type, so the excess electrons will not be there, but the process in the combination process, a trivalent atom readily creates the acceptor of impurity that creates the holes. So this is more positive, and then it is so called a p-type material. So let us move on to the basic CMOS technology. So the CMOS technology, complementary metal oxide semiconductor technologies. So you may be asking a question like why PMOS it cannot be implemented separately, and why NMOS. So actually, when you just at the right top corner, you can see the pull-up transistors as well as the pull-down transistors. So these pull-up and pull-down transistors, which are actually arranged between the VDD, the supply voltage, or the supply rails as well as the ground rails, it actually provides like a barrier that the VDD or the supply voltage line will not be connected to the drain, or sorry, the earthing or the VSS directly. So most of the time, the power dissipation can be stopped by using this type of arrangements. So when the VDD supply voltage or the VDD supply voltage rail is connected to the output, we will be getting the maximum output. And when the output terminal is connected to the ground via this NFETs, that is the pull-down transistors, we will be getting the minimum outputs, that is logic 0. That is how it has been arranged. So this, just below this, we can see some of the examples like CMOS inverters, MOS, NAND gates, NOR gates, AND gate, as well as OR gate structures. So the CMOS is actually the combination of both P-type MOSFET as well as the N-type MOSFETs, and it will be arranged in such a fashion like the pull-up transistors, which are arranged close to the supply voltage rail, and the pull-down transistors, which are arranged close to the ground rails. So here, pull-up transistors are made of P-type transistors, and the pull-down transistors are N-type transistors. So here, when you compare the mobility of these two transistors, this P-type is much slower than this N-type. So here, as we know that this MOS transistors are actually minority carrier devices. So the P-type material or the P-type MOSFETs, the holes are the carriers, and here the electrons are the charge carriers, actually, minority carriers. So here, when you just consider this inverter structure, so when you are applying a very low gate voltage, so this P transistor is responsive, and this VDD is connected to F. so that we will be actually having a high voltage at the output. So when you just give the gate voltage high, what happens? It will be responsible. The N transistor will be responsible and P transistor will be cut off, so that the VDD and F will be actually open circuited, and F and ground will be just short circuited. So the dissipation of the gate capacitance, that will actually lowers the output at the F terminal, and we will be getting a logic 0 or low at the output terminal. So that is actually the complementary actions of this MOSFET. So the reason why actually they have used this is, so there must not be any direct connection between VDD and VSS at any time. So in any particular instance of time, it will not be connected directly. So that is why these transistors are actually working just like a voltage controlled switch, because the gate voltage has been controlled, and this condition of just having a short between this VDD and VSS can be stopped ultimately. So this type of MOS technology actually starts with the fabrication processes, this technology process, CMOS technology process. That is the, there are several stages like crystal preparations, masking, as well as photolithography process, depositions, and implantation processes, diffusion processes, as well as oxidation, metallization, and packing. So these are actually the processes which are involved with the VLSI technology. So first thing, we need to create a wafer or a die structure which need to be created, and over that the active and passive components of electronics has been integrated. For example, if you want to just create a diode or a transistor structures or an interconnect, or if you want to just create a capacitance, so over that die it will be done. So here the crystal preparation is a basic thing, and we have already studied our, hopefully you may know about the Swarovski crystal process, growth process, as well as the float zone processes of creating different types of silicon materials. And we'll be using a seed crystal, and we will be just using some crucibles where we can just mold the silicon, and the seed crystals will be introduced into that mold, and it will be just withdrawn, and the crucible as well as the lead will be rotated in an opposite direction, so that a crystal, a cylindrical type of crystal structure that can be formed, and that will be withdrawn so that it will become just like a crystal ingot. So from that crystal ingot, we can actually slice it and we can create circular discs. So those circular discs can be further divided into several rectangles, and those rectangles can be viewed as a die. So in this, the die preparation process, we have to just maintain the purity of that silicon. Otherwise, if there is any such impurities, that will actually lead us to certain conditions. So the next phase is the masking, actually the masking processes. So why do we actually go for a masking? So as I'm just going through the very basics of these things, just telling why do we actually go for this masking. So we want to just, if you want to just imprint the mask patterns or the patterns or the gate structures, if you want to just imprint the circuit patterns over the silicon structures or the substrate wafer, so we are supposed to have the active as well as the passive masking. So the different types of masking is active and passive masking. So we will be actually using a silicon dioxide layer and along with the photoresist. So this photoresist actually has two types. The first one is under ultraviolet illuminations, the photoresist can make a coagulant, and this coagulant can be stripped off or it can be etched out. Otherwise, the passive masking means, and it will actually really harden when the epoxy structures will get hardened, and the remaining part can be stripped out, so that those part which has been hardened, that can be used as a potential mask, and it will just try to protect the region underneath. So this is a preliminary process that can be done before the photolithography process. So the lithography process, which includes the imprinting of the mask patterns over this particular silicon substrate. and where we have to just selectively go for some implantations or diffusion or oxidation processes. So that can be carried out after this photolithography processes. So 3 processes that can be repeated in between every stages. The first one is a photolithography process, masking lithography processes, and then followed by the etching process. So these 3 processes will be carried out in order to just customize the mask, as well as in order to just give the area, the dimensions where it can need to be implanted or diffused, or if you want to create any epitaxial growth or any epitaxial layer or a polysilicon layer, that can be customized using that. Lithography is actually a process. We will be having a chromium slit or a plate which has the slits, or the mask patterns will be drawn in the form of a slits. And when it is after the photoresist placing, after covering the entire surface with the photoresist, we will be actually just allowing the placing the chromium plates, and the chromium has the tendency to stop the ultraviolet radiations, and we will be just allowing the entire setup for the ultraviolet illuminations, so that this ultraviolet radiations that can be just striking the photoresist in the open areas or the exposed regions. So in this case, these this ultraviolet radiations, it will actually create some coagulants in case of active mass, and those coagulants can be stripped, so that the mask patterns can be implanted over the or imprinted over the substrate. And the next process is the implantation process. What is the implantation process? Implantation means we are adding. If you want to have a very shallow diffusion or a very shallow region of impurity atoms, or we can go ahead with the diffusion process, because in diffusion we will not be using any acceleration process. So the impurity atoms will not be accelerated, so that the depths cannot be attained in this. A shallow diffusion layer can be followed or formed by using this diffusion process. And the implantation process, for example, if you want to create a N-type or a P-type well form structures, or a source or a drain structures formations, sub-formation, N-type or P-type formations, we will be going ahead with this implantation processes, where the trivalent or the pentavalent atoms, based on the requirements, like whether we need a N+ type or a P+ type, we will be taking that into account, and we will be selecting the impurity atoms, and it will be actually accelerated to very high velocities, and it will be bombarded over the surfaces of that exposed silicon layer. So what happens means the bombardment creates destroys that entire top layer, and it will be penetrated. And because of that, the impurity atoms will be actually going deep into that surface region, and it will be staying there actually. So when it is just penetrating into the substrate, and it will actually have a lot of collisions, because actually there is a process called the Monte Carlo analysis for the path. So identify the path of each and every impurity atoms. It travels within the silicon lattice structures. So it actually goes with a lot of collisions, elastic collisions, and finally it comes to rest. And when you just see the doping profile, and when it is actually nearby that masked regions, at the edges of these masked regions or this open exposed regions, so the concentration of the impurities are very much lesser. So the process is, when we are actually just doing this implantation process, since we are accelerating the dopant with a very high velocity, and we are actually bombarding it, we cannot control the movement of these particular impurity atoms into the crystal lattice structures. So some of the most of the doping profile, the concentration of the impurities is much higher at the central level, and it actually diminishes towards the edges of these mask patterns. And when it's underneath the mask patterns also, there are some chances of just moving or the settling down of the impurity atoms. Okay, so The next case is the diffusion type. Diffusion is already said. We can use diffusions to just take or create the shallow well formations and all. Oxidations, as you all know, it will be actually creating the silicon dioxide layer. Also, that will be used as a mask, or it can be used as a in the gate oxide between the gate polysilicon region as well as the channel. And finally, metallization. Metallization is the process which actually makes the interconnects between the transistor structures. So the metallization, we can use the increase the resistivity of any particular area or through this interconnects, because it will offer sheath resistances. So we can actually create the capacitive structures if you are actually just separating this to metal regions by using some insulating material. We can actually create the capacitances, increase the capacitances or no. So actually there is a process called placement and routing. While that's an interesting fact actually with the CMOS technology. So highly demanded transistor structures or highly demanded logic blocks are being placed nearby. So if in order to just reduce the interconnect, the distance the usage of the interconnects. If the interconnects are being used much, automatically it will increase the latency at the output, because it will offer high resistance. As well as the capacitance, the parasitic capacitances will also be induced, and that will actually degrade the performance of the integrated circuits. So immediately after the floor planning processes, we will be actually having the placement and routing strategies. So that is actually a very interesting fact when it comes to the CMOS VLSI design. And finally, we have to pack. We have to actually create the input-output pads, and we have to just pack this this die structures clearly, because the radiations that can excessive heat or radiations that can violate or that make this structure malfunction. So in order, we have to just create create clear ceramic pack, and we will be actually packing it, and it will actually takes the IC will takes the final shape. So actually this is the inverter. We have already seen all these things, and I have just given the oral skeletal view about this technology processes, and this is a sectional view of CMOS inverter structures, and you can see the CMOS gate structure here. So this is a P substrate, and over which we are actually creating an N-well for creating a NPN type of transistors here, and this is PNP type of transistors here. So here in the P substrate itself, we will be actually having the NPN type of transistors, and we have used the same base structures, same P type substrate or base or bulk, we can say it, I represent by it with any terms. So that this region, this A, it is marked as A, it is actually called as the gate or the regions, gate regions, and this is actually the drain and source region. So here, the blue color, it is actually shown as the metal layer. So here this black color is shown as the polysilicon layer, and it is a polysilicon gate over which the gate voltage will be applied, and the conduction between the channel formation between the drain and source that can be controlled by that. And this is the cross-section and the top view of the mask patterns, the inverter mask patterns. So this is the cross-sectional view of a CMOS inverter, and this is how it looks like when it's seen from the top level. So you can see some rectilinear portion, black color rectilinear portion, that is actually called at the middle. That is at one side it has been mentioned as NMOS transistor, and the other side it is mentioned as PMOS transistor. So that is nothing but polysilicon gate actually. So here there are some squares, black colors are there, right? So that is actually called as the contact cuts, so that over which the the substrate or the silicon layer, it's getting in touch or contact with the metal layers here. So the blue color layers which has been shown here are metal layers, or that can be the interconnects of that. Okay. So here it is shown as the surface trap and the well trap, and The mask views. So these are the different mask views that can be used at the formation of this particular transistor structure. And at the first level in the N-well formation, so this is the area where the N-well need to be formed so that it is used to create that PNP type of transistors. So this is the area or the exposed region which will be allowed for the ion implantation. Just to see the top of this. So this is the area where we can use this particular mask pattern for N-well creation. And the second mask pattern is actually a polysilicon layer creation, and followed by N plus diffusion. These two are the N plus diffusions, and P plus diffusions area. This is the P plus diffusions, and followed by these are the contact cuts. So how the metal is actually getting in contact with the silicon substrate. And finally, metallization processes. And metallization, there is a specific process called sputter process. So generally aluminum can be used for that, aluminum or silver can be used for that. So generally this aluminum can be just sputtered, or it will be using directed towards these molecules are directed towards this particular places, and it will be settling down here. So here this is the mask pattern which is contributing for that metallization processes. Totally there are 6 type of masks. First one, this is the first one which is used for the N-well formation, and this is the second one which is used for the polysilicon formation. And this is the third type, which is used for the N plus diffusion formation. So here we will be using the ion implantation process here for the N-well as well as N plus as well as the P plus diffusions. And this one is used for the contact cuts. So to make the metal as well as the semiconductor contact. And the final one, this blue color shown, this is actually used for the metallization process. So let us move on to the micro electromechanical systems. So in the CMOS type, CMOS technology, we have just studied about the basic semiconductor, the wafer from the wafer preparations as well as the basic technology process, VLSI technology process. So which stated about the masking, photolithography, depositions, implantations, diffusions, oxidations, metallization and packing. And we have seen the cross-sectional view as well as the inverted mask sets, and followed by the detailed mask views, which has been incorporated with this making of this particular CMOS inverter structure. So this is actually the basics of that one. Right? So next we can just go to the micro electromechanical systems. So the speaker actually shows that what are the actions which has been incorporated along with the micro electromechanical systems. So it is actually comprising of a mechanical sensors or any sensor arrays. So it's like application specific integrated circuits like computing units, and followed by the actuators, the micro actuators are there, actuator arrays are there. So the sensing it's been done, and the actions actions can be executed by using the mechanical actuators. And here you can see that the input as well as the output. So the inputs and outputs are the responses of the sensors, and inputs are the triggers of the sensors actually. So often referred to as the microsystems technology, fabricated using modified silicon and non-silicon fabrication technologies. Here almost the fabrication technology which has been used in silicon structures that can be adapted here. Process technology used to create tiny integrated circuit devices or systems that combine mechanical and electrical components. Our normal, even into our mobile phones, we are actually using the proximity sensors or some gyro sensors like so tilt sensors, and most of the sensors actually comes under this micro electromechanical systems, and it's actually using the semiconductor devices. That's why we have incorporated this particular topic into this presentations. So these devices have the ability to sense, control, or actuate on the micro scale and generate effects of the macro scale. So we can actually sense, and we can just use the actuators, sensors. The sensor out inputs are actually given as the data acquisition, and it is actually known to identify the various changes which happens with this atmospheric conditions and all. And based on that, the actions that will be triggered by using the actuators. So the components of micro electromechanical systems are microsensors, micro actuators, and microelectronics, as well as the microstructures. So what is a micro actuator? It acts as a trigger to activate external devices. So a microelectronics will tell the micro actuator to activate the device, because the microelectronics is the one which actually processes the signals which is being just given as a input to this particular by this particular microsensors. So extremely small structures like built onto the structures, they built right into the next silicon MEMS. So these are actually termed as the microstructures and microsensors. So gather the information for, as I told earlier, already it is used for the data acquisition processes. So what are the signals that can be monitored, like mechanical, thermal, biological signals, as well as chemical, optical, and magnetic readings that can be monitored by using this. So when you just ask the question why MEMS we'll be using, because of its size and its low power consumptions, and it's more sensitive towards the inputs and mass production when it comes we have seen that, we might have seen that all the sensors in outputs, I mean the sensors, the rate is actually cheaper, less invasive than the larger devices. So for all these particular advantages, we will be using this micro electromechanical systems. So the design process of this MEMS actually has the deposition process. So ability to deposit the films of material on the substrate, and followed by lithography and etching. So all these three processes that we have already seen with that silicon process technology, or VLSI technology, sorry. So here this the process is just the same, but the materials that we use only differs here. To apply the pattern mask on top of the films by photolithographic imaging. So etching, what is etching? Actually, to etch the films selectively to the mask. A MEMS process is usually a structured sequence of these operations to form the actual devices. So we will be having the different types of etching, like dry etching, wet etching, and plasma etchings is also there. So in order to actually go for a isotropic or anisotropic etching, so based on the requirement, actually we can just classify, or we can customize this particular, or we can utilize this particular types of etchings and all. So in this design processes, the process of the deposition of material, pattern transfer, removal of material, and everything, it is shown here, and probably it will be lead to the probe testing, sectioning, and then individual die formations, assembly into package seal, and final tests. So these are the process technologies, just like the process flow that we have seen moments ago. So in this case, the materials used is generally silicon, polymers, metals, as well as ceramics. Metals for the interconnection, ceramics for the packing, and polymers for the interconnects and gate structures, as well as the silicon, which is used as a base material then. So here the surface, the two fabrication techniques for a silicon type of micro fabrication, surface micro machining is there, as well as bulk micro machining is there. So, so here the selective removal of underlying films refers to as the sacrificial layer. That is actually important in the case of surface micro machining. So we will be just seeing that. So here you can see in this figure on the right side, right edge, you can see the substrate over which a sacrificial layer is there. So here over the sacrificial layer, we can form some structures, mechanical structures over here. And just to see the last figure, you can see this green colored layer has been stripped off. So this layer is actually called as a sacrificial layer. So it will be used to create such type of formations or microstructure formations in the over the silicon substrate. So the next one is bulk micro machining. So it's just an extension of IC technology for the 3D structures. Actually, bulk micro machining uses actually dry as well as the wet etching techniques. So here the wafer bonding as well as the deep anisotropic dry etching. So these actually are the significant processes, and it will add as additional process techniques along with that. Normal the etching as well as process technique. Wafer bonding means actually the stacking of wafers as well as anisotropic etching. So we actually want to just set clear boundaries to that etching we have that need to be performed. So reactive gas plasmas can perform deep isotropic dry etching. So this is a type of a chemical etching also. So this gas molecules will be directed towards this particular area. So it will create it will react with that surface and it will be just eliminated. So here you can see the bulk micro machining. So isotropic, and this the difference between this isotropic and anisotropic etching. So isotropic etching, you can see the layer beneath this mask patterns also it is being etched. So there is no control over this particular type of etching. So anisotropic etching, because it has been controlled. So you can see some small tapping over this area. So this trench has been formed exactly within the boundaries of this particular exposed region. So here, extra removal of material, it is happening in the isotropic etching. So this isotropic etching is, in some cases, it is preferred, but most of the cases, with this precision, for a precise, exact conditions, we have to use this anisotropic etching. So what is the wafer bonding method? That involves joining two or more wafers together to create a wafer stack. So direct bonding is there, anodic bonding and intermediate layer bonding is also there. So this deep reactive ion etching, it is actually called as the high aspect ratio fabrications, and it's especially for the silicon structures. So here, in using this LIGA is actually a German acronym word, lithography, galvanoforming as well as abforming. So it is meaning as lithography, implanting, plating as well as molding. So it is actually used to create some structures over the seed area or the seed material. So in the next, we use the X-rays instead of the ultraviolet radiations. We will be using the X radiations, and by using in this particular type of lithography process. So you can see here. So PMMA is a type of plastic polymethyl methacrylate. So here, this is the sacrifice layer, and over this seed material is there, and it is just grown over the surface of that. So this PMMA is actually used as a mask layer. So it will actually it will be using as a protective layer here. So this mask layer, this is the active mask region. So the X-ray illumination is there. So when it is actually exposed to this X-ray illumination, this will form a soft type material so that it can be stripped off or removed by using etching. So after that, we can actually create the electroplated material that can be implemented over here. So over the seed material. Okay. So this is the general process which actually uses this LIGA. So that can be shown here. So the next process is the MEMS design process. Design process is a packing. So protect the sensor from external influences and environmental effects, and protect the environment from the presence of the sensor. Provide a controlled electrical thermal, because the environmental conditions, because it will be directly fixed with the facing the environmental conditions. So the excessive heat or some moistures actually can degrade the performance of that. So we have to protect it from the environmental issues also, external influences also, electrical, thermal, mechanicals. So these are the basic things. So these are some of the applications of the MEMS in different areas, like vital areas like automotive, automobile regions, electronics, medical, and communications, defense, and everywhere we can actually see this type of micro electromechanical sensors and its applications and all. So generally, we actually have the pacemakers, right? We might have heard about the pacemakers and muscle stimulators. So here, this rate responsive sensors, everything, we can actually have this type of micro electromechanical sensors. We can use this. So let's move on to the system on chip overview. Actually, so it is one technique which actually integrates all the components like CPU, GPU, memory into a single integrated circuit. So that is actually system on chip. So here, so it actually there's a with some internal frameworks, the presence of multiple modules interconnected via internal bus or networks, that is actually called as the internal frameworks. So within the single memory chip, or not say a single circuit structure. So actually we can integrate all these CPU, GPU, memory, input output devices, peripherals, power management systems, and clock and resets, signal processors, and other things by using the inter-module communications methodologies, and we can put it into a single chip, and that is so-called the system on chip. Okay. So there are some key processing units with this system on chip. So actually it has the central processing unit, and serve as the main component of responsible for executing instructions, performing calculations and all, and controlling the overall system functionality. The functionality of the entire system that can be controlled by using this CPUs. So depending on the requirements, the CPU can have multiple cores of parallel processing elements such as ARM, RISC-V, 86, and other custom architectures. So based on the demand, it can have a single core or a multi-core configurations. Okay. So the next one is graphical or graphics processing unit. The graphics processing units plays a vital role in the SoC systems by managing the graphics computations, and while usually utilizing any image or video processing operations, or any graphical computations commonly used in gaming, AI, and image processing, that we can and other multimedia applications also, we will be using these graphical processing units. So this will actually provide a smoother visual experiences. So the role of this particular GPUs are to provide a smoother visual experiences and all. So the performance of these systems can vary based on the target applications. Okay. So we can use the third-party vendors licensed, grab GPU designs also. For integrations with our SoCs, we can use third-party vendors, GPU systems, authorized GPU systems also. So as I told earlier, that is based on the target applications, the functionality may vary. It can be changed. Okay, for a specific systems, and for the other chip designs also. So digital signal processor optimized for signal processing tasks like audio and video encodings. So for this processes, we will be using a digital signal processor and AI accelerator also, specialized for machine learning and deep learning tasks. If you are using a neural networks based systems or decision making or decision support systems, we will be using this AI accelerators too. So the next one is memory. We can actually have the random access memory, SRAMs, and used for quick access of data on instructions by the CPU. And we will be using the DROMs also. So actually in this cases, we will be actually having the input-output interfaces, the data transmission, communication with the external device, and that will be actually directly given to the memory also. So here, so in this system on chip architecture, you can see the central processing units followed by the GPU, data processing hardware accelerators, by the RAM, the system memory is there, interfaces, external DRAMs can also, DDR4 or and we can use the non-volatile memories also for firmware storages. So here, this interconnects, when we actually go ahead with this interconnects, actually we have several, bus system, that is actually advanced microcontroller based architecture, AMBA. So this architecture is actually used for custom interconnects for data exchange between the internal components. So as you see, you can see it is in the figure, this TMA bus master, it's there. It will be actually driving these particular structures. So here the high performances, ARM processors and everything that can be used by this AHP. And it can be utilized for data transfers or coordinations among the CPUs and memory, GPU peripherals, and input-output interfaces. So here we will be using another one structures called a network on chip, and that can be used for establish interconnectivity within the SoCs also. So the next one is peripherals, input-output interfaces, GPA, general purpose input-outputs, UART, SPI, I2C, and CAN protocols, etc. So we'll be using the peripheral components, using the interrupt controllers, as well as the serial communication interfaces like UART, SPI, and I2C. So here the timers, analog digital converters, digital to analog converters, and various controllers that can be utilized. So why we are actually using this peripherals to, it is used for the enhancing the performance of the or the functionality of the SoC and enable to have effective interactions with the external devices and systems. That is why we are using this peripherals too. So the power management systems will be utilized for optimizing the power usage for the effective distribution of power to different SoC components that can be used, adjusting the voltage levels and power states based on the workload and system requirements that can be used. So here, this is actually a self-test mechanism which has been incorporated with this SoC design. So debug and test features, JTAG, joint test action groups. So here we will be using the trace buffers for performance monitoring systems actually. So this particular structure is actually used for design, debugging and testing of these devices. So just like a BIST, built-in self-test. So these are the different types of SoCs, like applications SoCs used in consumer electronics like smartphones, tablets, and laptops. And if your embedded SoCs, applications like automotive systems, industrial automation systems, and all. Heterogeneous SoCs, the combine various types of processors like GPUs, AI accelerators. So this will be heterogeneous SoCs actually focuses on maximizing the performance of the specific workloads. And then FP field programmable gate array based SoCs combine programmable logic with fixed function processors. So these are actually the types of SoCs which are in. And then comes the SoC design process. So actually, this design process is majorly classified into two. Actually, the front-end design followed by the back-end design. Back-end design is actually called as the physical design. So front-end design is the high-level modeling as well as by using the Verilog or VHDL, like some programming languages, high-level languages, hardware description languages. We can just design the netlist, and we can actually go ahead with the functional simulation and verifications. So before implementing these devices, we can actually go for the testing process. So like whether the circuit that we have generated will be actually functioning properly or not, that we have to just ensure. So that type of ensuring that can be termed as the simulations. We will be actually not giving the exact I mean the real-time inputs, but we will be actually creating such type of some inputs which are equivalent to this real-time, and we will be actually providing it as an input trigger, and we will actually expect the responses of this particular circuit. So that process, the functional simulation and verifications, so that is the software testing and refinement. If there is any such refinements are required, we can do it at the stage itself. It's a stage itself. So this RTL synthesis and DFT. So in this, the gate level netlist can be prepared after this resistor transfer level. register transfer level. So the next one is the physical design process. So here the floor planning has the floor planning, and followed by the logic placements and routing, clocking strategies, and then the routing of this BSS as well as the BDD lines, and timing analysis and signing off, and physical verification and sign off. So timing analysis. So actually this deals with the clocking strategies and all. So the physical verifications, whether the circuit is actually performing good and or everything it has been working, the functionality of this entire device will be tested here, and it will be given the sign off. So the design process includes the specification definitions, processing power, memory, peripherals, what are the actually defined requirements of these, the power consumptions, etc. So we have to identify the target applications and constraints. What are the constraints that we have? Sometimes we may be having the timing constraints, or maybe the resource constraints we have. So the designs can be classified as two different types. The first one is non-constrained, as well as the second one is constrained type. So constraint major is the resource constraints as well as the timing constraints. So based on the target applications, which type of constraints will be there, and based on that, what are the specifications required that can be defined at this process itself. The architectural design. So functionality into processing, memory, and interconnect components. So we have to just customize or we have to define the architectures fully, and decide on the processor types, which processor that we are going to use in this case. So IP blocks, IP selections that can be done next, ensure the compatibility of IP with the chosen interconnect protocols. So that has also been very important here at this stage of design process. And followed by the simulation and verifications, the validations of SoC functionality using simulation tools like System Verilog. So as I told you earlier, that the state timing analysis that can be taken, so that in case of any unwanted usages of this hardware materials, that can be avoided, or duplications of this can be avoided. The functionality can be ensured here. So whether it has been done properly, the functionality is actually proper, it can be validated here. So the physical design is what we have already created the net list and all. So the circuit is already been created. So we have to translate that into the physical layout. So optimize the area, power, and performance. So all these three are interconnected. So if there is any changes with this area, that will actually change the power, and that will actually give the performance, improve or enhance or degrade the performances of this particular circuits. So fabrication, send the design to manufacturing unit or the fab houses, and use advanced processor nodes like 5 nanometer or 3 nanometer for high performances design. Okay, this is actually the feature size. The 5 nanometer or 3 nanometer is the feature size of this device. And testing and debugging, design for testability, and uses JTAG, BIST, as I told, built-in self-test. So when it is coming to the market, we will not having the testing processes. So it will be a part of incorporated along with this. Separate area to be allotted for this, and we will be actually having the scan chains for that. So the responses will be actually taken, and it will be actually placed in the scan chains, and for the comparison and the improvement of this particular. So automatic test equipment to validate the fabricated chips, everything that can be done at this stage itself. So finally, the software developments. So that's all about the design process of SoCs, and we have seen the CMOS design flow process, the process technology, and after that we have seen the introductory part of the MEMS, micro electromechanical systems, and then we have just studied that we've seen that system on chip, the fabrication processes, the design processes of SoCs, and what is SoC and what are the different types of peripherals that we can utilize there. The next one is FinFET. So FinFETs can be used for faster applications, and when compared to its low power utilization and smaller size, we will be using this FinFET most of the um, modern applications and modern systems, smart systems, and it has its handful advantages also, as well as the disadvantages also. We'll see it in the later slides and all. So I'm not going much deeper with this FinFET. Actually, this this is generally created over this silicon on insulator type. So we have the advantages of this using this FinFET is actually we can have two gates structures, so that the control over the gate voltages that can be maintained much precisely more than the MOSFET. So that is the added advantages of using this. So here the comparison over the MOSFET and FinFET, it is there. So the planar MOSFET, so this is the cross-sectional view of a planar MOSFET. So it's an NPN device. So actually the length of this channel L and the oxide layer and metal, it's a single gate. So less control over the channel. And the leakage current, the subthreshold leakage or the second order effects will be there. But here the second order effects will be nullified, because when comparatively it is less leakage, because it is created over the this one insulator type. So here there are the formation of two gate structures that can be formed here. So so that the control over the channel, it's actually very much maintained here. And this is the top view of the FinFET. So in this FinFET, we will be having different types of fins, like not different types, we have the similar types of fins like structures. So this actually fins plays the role of a source as well as drain. So that can be controlled by using a single gate strip. So excuse me. So that can be controlled by using a single gate strip. So you can see the figure below. So the gate strip, it is actually having the various numerous numbers of the fins-like structures. So that is actually called as the source and drains of the transistors. So broadly, it is being classified as a short-gated FinFET as well as the insulated gate FinFET. So here the gate structure, which is common. So this is a short-circuited gate FinFET. So both the gates, gate 1 and gate 2, are being short-circuited here. So here, this is the structure which actually tells us about that. So and the insulator type means you can see this gate 1 and gate 2 are completely isolated by using this dielectric. So SOI type as well as the bulk FinFET, these are the two other classifications. So here the silicon substrate, which the source and drain can be just created by using that same silicon substrate, and here the oxide layer. So that will be actually placed, the silicon and the source and drain will be actually created above the oxide layers, so epitaxy layers, so that the isolation can be perfectly done by using this SOI. But when it comes to this case, the isolations cannot be, it will actually have their own second order effects and all. So as I told, it has having some handful advantages and disadvantages. So better, when we concentrate on the advantages, better control over the channel, suppressed short channel effects is there, and lower static leakage current is there, as well as the switching speed can be improvised, as well as drain current, and lowering the switching voltage, low power consumption. Ultimately, it is used for faster switching speed, as well as control over the channel, as well as the low power consumption. And it's a smaller size as well. So the next, when you come to the disadvantages part, it is actually having higher parasitic due to 3D profile, and because the capacitance, the parasitic capacitances is maximum, very high capacitances due to the dual gate layers. It is actually experiencing a lot of capacitive effects actually. So corner effects. So electric field at the corner always amplified compared to the electric field at the side wall. So it can be minimized by using nitride layer at the corners and the high fabrication costs. So generally SOIs have very high fabrication cost, and it's also it is not going to be a different one than that also. So it is actually experiencing high fabrication cost. Because of that, these things, it can be used, even though it has a very good advantages, it will be used a little bit as per the application requirements. It can be used. So in this presentation, I have actually taken the very basic things, since it is the introductory lecture. So I have to just, I have taken the very basic things like what are the semiconductors, the role of semiconductors in modern day smart systems. And I started it from the CMOS technology, and from the CMOS technology, what are the design process flows and everything we have just seen, and followed by the microelectromechanical systems. So microelectromechanical systems, and we have not gone much deeper into that, as it is the introductory part. We have just seen only the basics of the fabrication processes and all, and we have seen the different types of the process flow, like deposition, lithography, as well as etching processes and all. And then we have just seen the basics of SoC, silicon on chip, system on chip, sorry. And in that, the process flow, also the design flow, the basic physical as well as the front end as well as the back end design, I mean, design flow that we have just seen. And finally, the FinFET. And we have not gone much deeper into this. We have just made a comparison over the modern day MOSFETs, and how it is actually more advantageous over these MOSFETs and all. We have just seen. And thank you so much for your patience and for your valuable time. And hereby I just conclude my presentation. Thank you so much. Am I audible there?
Yes, sir. Audible, sir.
Okay. Thank you, sir.
Completed your presentation?
Yes, sir. I have completed.
So some professors have raised their question in the chat box. Shall I go through it one by one, sir?
Let me just see it.
Yes, sir. Just you can see and answer them properly. Thank you.
I have got a lot of questions from Naga.
Yes, sir. Professor Naga Sadhya Narayana Murthy, sir.
How to identify the cracked or damaged dies after wafer preparations? So that is actually there is a fact called yield. So we will not be considering those cracked or damaged dies after wafer preparations and all. Will be. So can you please do one favor for me? Actually, can you please share my email ID with this professor? So I will have a discussion with him.
Okay, sir. I will share your email ID.
Okay, and my contact number to the professor. I will be just having a discussion, because I have he has raised a lot of questions to me.
Yes, sir. Once we complete our technical sessions of today, I will share your email ID to the participants via WhatsApp group.
Okay, sir. We'll discuss actually.
Sir, can you turn on your camera, sir, please? Okay, thank you, sir.
Thank you.
So, at first, I want to thank Professor M. Prasutha Arthi, HOD of Artificial Intelligence and Data Science, for the warm and comprehensive introduction on today's technical session expert. Next, I would like to thank our today's technical session resource person, Dr. D. Jnana Jabada sir, Assistant Professor, Faculty of Engineering and Technology, Villa College, Q1 Campus, Maldives, for delivering a highly insightful and enriching session on Introduction to Semiconductor Devices and Material for Smart Systems. Your lucid explanations of complex semiconductor concept and FinFET structure gave all the participants a strong foundation for the upcoming sessions of the ATAL FDP. The way you connected fundamental principles to real-world smart system applications was truly commendable. I am sure that our participants greatly benefited from your depth of knowledge and engaging presentation. Now, I invite Dr. R. Hemalata Madam, HOD of Biomedical Engineering, to deliver the vote of thanks for the technical session 1.
Thank you, sir. Good evening, everyone. On behalf of organizing committee, I take this opportunity to extend our heartfelt gratitude to our distinguished speaker, Dr. D. Gnanasabadas sir, for delivering such an insightful lecture on Introduction to Semiconductor Devices and Materials for Smart Systems. Your valuable knowledge and practical insights have enriched today's session and will certainly benefit all participants in their academic and research pursuits. I also wish to thank our managements, principal ma'am, and faculty coordinators and all participants for their active involvement in making these sessions successful. Thank you, one and all.
Thank you so much. Thank you.
Thank you, sir.
Thank you, madam, for your words of gratitude and appreciation. I request all the participants to stay online for the next technical session 2. The technical session 2 will start sharply at 8 p.m.
Sir, I have one doubt, sir. Sir, for session 1, attendance link will be posted or not?
So once we complete both the technical session 1 and 2, we will post the feedback form for both the sessions, sir, via WhatsApp group.
Okay, sir. Okay. Thank you so much, sir.
Okay. Once we complete both the sessions, I will share the feedback form for both the sessions via WhatsApp.
Sure, sir. Thank you, sir. Thank you, sir.
Good evening, everyone. It is my privilege to introduce the expert speaker for this session, Dr. Neeraj Kumar Misra, Associate Professor at Belur Institute of Technology, AP University, India. Dr. Misra has more than a decade of experience in teaching and research and is a senior member of IEEE. He completed his PhD under TEQIP2 and a World Bank Fellowship at Dr. APJ Abdul Kalam Technical University in 2017. He also pursued a postgraduate diploma in machine learning and artificial intelligence from NIT Warangal. His academic and research achievements are highly commendable. He has authored or co-authored over 50 publications in SCI and Scopus journals, written 3 international books and 15 book chapters, and presented paper at prestigious conferences. He is also the inventor or co-inventor of 7 Indian patents and 3 international patents granted. He has received AICTE grants under FDP and MODROP schemes and has guided several postgraduate and doctoral students successfully. His current research interests include quantum computing, reversible computing, nanomagnetic logic, fault-tolerant architectures, and low-power VLSI design. Today, he will share his expertise on device-level innovations in semiconductors for AI and IoT. Please join me in welcoming Dr. Neeraj Kumar Misra. Thank you all.
Okay, sir. So
thank you, sir,
thank you
for
very
the
much.
detailed introduction. Okay, can I unshare my content, sir, please?
Okay, sir.
Yes, sir.
Okay, so thank you very much, sir, for your nice introduction about me. So now I am Dr. Neeraj Mishra. I am the associate professor at VIT University, and today I am going to discuss about the innovations, what research is going on in the VLSI field, and what is the design methods to design ultra low power circuits in terms of okay, sorry, very sorry, actually some interrupts is there. So now I need to share my screen, and then I will start my presentation. Okay, please let me know my screen is visible.
Yes, sir, your screen is visible, sir.
Okay, thank you very much, sir. Okay, now, okay, so now today I'm going to discuss about the semiconductors, means what are the research trends is going on in semiconductor, mainly the MOSFET and some advanced device architecture. Okay, and how this AI field is helpful for the device performance more better. Okay, so that is my agenda of lecture. So in my presentation, I will discuss the introduction part, what is the past trends, what is the current trends, of VLSI and what is the future perspective of VLSI, and then conclusion. Okay. Now, first, I'm going to discuss the very exciting news in the VLSI. I think everyone have aware about this news because now, previously, the India is designing like Taiwan is basically leading the manufacturing part, but now, according to the present scenario, the India is also going to do the manufacturing part in our country. So there is a very good news around more than 3 lakh professionals required actually in the manufacturing side, like device level. So that is a shortage actually in 2027 because many of the fabrications lab is stabilized in our country because we have to fulfill the government scheme like Atmanirbhar Bharat and Make in India and Digital India. So if we do the manufacturing part in the country, then it's more development in terms of device level. Another was we have the semiconductor industry. It means the employee salary is around 3 times more than software engineers. It is a new in this art means in the but you can see because the semiconductor industry is more as per salary point of view, it is more actually. Here means a great engineers required to manufacturing. That means it skills actually. And now the government is investing more to stabilize a fab in our country. So they have given around more than 27,000 crore fund to stabilize the fab in different. Of course, many big companies there like Tata Group and Intel is also planning actually to manufacture chip in our country and target actually around 8 billion chips per day. So that is very high capacity. Is manufacturing take a lot of chip in industry in a one fab. So that new federal government is seeing like in conductor futures. So you can see development is already started state like which is means Tata investing around 91,000 crore fund to make a semiconductor fab. So the Micron, the Micron is also looking the fabrication part, and here this company is also investing more fund means to make a fab lab actually. Okay, so we can see here many big companies is coming here in our country for stabilizing the fab industry. So that is a great opportunity. Okay, so I'm very sorry for interrupt. I think from internet
No
issue.
issue, sir. No issue.
So okay, so now I need to share my screen. So now I'm going. I discussed about this exciting news in the VLSI. Many of the fab industry is stabilized in India to make to make a device. Okay, so that means we are going to manufacturing actually. Many of the companies stabilize the fab lab in many different states. So other interesting news in the national quantum mission, we know this is stabilized in this year, and this national quantum mission is working on the 4 vertical direction. These are the directions, and this quantum computing is very helpful to make a, device more powerful, more faster. Okay. Now I come to the previous trends. Basically, we know the IC is controlling all the parts like computing device. Every computer have a IC, and all the mobile device or all the signal and imaging devices have a IC. So IC is the central part to control everything. Okay, so if we come to VLSI, means many of the device in a small area. So in VLSI, there are 3 more important parameters. One is area, power, and performance. So, but these all parameters are uncontrollable. Means if we reduce the area is half, the power is going in not linear, is go to y by root 2. At the time, speed is 2 times. Okay, so in VLSI, the main goal of to design any complex circuit is minimum area, high speed, low power, and low cost. So the low power is depends on the static and dynamic power must be very less, and also the leakage power will be also less. Then we can say the device is low power. And if we come to the low cost, it depends on the manufacturing cost, means the lithographic cost, because in the manufacturing side, around 20 steps are there to make fabrications. So this lithographic cost must be less, then the chip will come to the low cost. So now the what is Moore law? We know the Moore law means every 2 years the transistor will be double, means 2 times. So that means that circuit is more complex. So many of the, I mean, you can see the trends of LSI. Previously, we are using a vacuum tube. That times the device is very bulky and it takes more cooling also. But the performance wise, the vacuum tube is not good. So after that, the silicon technology come in the market. This is more faster, around 100 times more faster than vacuum tube, and also it is very it means small size. So the whole VLSI means trend go very fast. At the time, more products is in the market, and many ICs also there like ASIC IC, SOC IC. So these ICs also very high performance using the silicon transistors. And if we go to the current research now, the nanotubes, carbon nanotubes based technology is there. And after that, the quantum technology is also here in the coming year, in this year, and this is more advanced. So you can see the what research trends is going on in terms of performance. And now in each field, you can see the ICs involved. Okay, computing device, mobile device, or aircraft or automobile sector. Everywhere ICs involved to control the signals. So first we see the trends. Actually means every IC is performing a multiple task. We know many signals are there, like digital signal, okay, like analog signal, okay, like mixed signal, okay. So a single IC is performing a multiple task. Okay, you can see this is the IC and it's totally packed with so the packet during means in the packaging we cannot see inside what are the transistors or devices are there, but pins are there. We can use the pin, okay, to perform a computation. Okay, now the IC. Okay, so the IC is actually go to PCB, okay, and the PCB go to system. Okay, this is a means we can see that broader level perspective. The system have a many chips are there. Okay, and these chips are performing a high computation task. Means we can say many complex tasks in a single IC. So if you go to the past trends, in the past we are using a multiple IC for different computing tasks. Like in monitor, there is IC, keyboard have IC, processor have IC. But this research is totally changed. So I means in this time, in this current trends, we have a single IC that perform all these operations, like Bluetooth or Wi-Fi or the means camera or keyboard. Every performance in a single IC. So IC is more compact. Now we see the ULSI engineer have many tasks like design, verify, fabricate, test, assembly, and deliver. So in different stages, many engineers are there, and all the work is different. So means because IC means there is a silicon wafer and it is bounded by a wire. You can see this is a wafer, and here many wires are there. Okay, so wires are actually connected, actually provide a routing to a signal to propagate the signal from one place to another. Okay, and after that you can see the total packaging is there in the top view, and we cannot see the wire and we cannot see the devices what inside the IC. Only the pins connections are there. So these are the actually the individual IC work, means many uh, stages are there in the IC. Now we come to the EDA tools in VLSI. So you can see many vendors are there. They provided a means electronic design automation kit to make a circuit and check the performance. So in terms of research point of view, many company has taken a patents for our product, that is a copyright. So in that case, the cadence is the dominating with all other EDA tools. But other vendor is also there like Synopsys, TSMC, IBM. They have already released EDA tools to create an environment in the tool and then test the design and the materials. If it is satisfied, then we have to forward this GDS2 file to fab industry for manufacturing a product. Because the manufacturing of product, it takes very costly. So that's why the EDA tool play a very important role to check the device performance. Okay, so you can see the industry is looking the IC in this way. Mostly the outer boundary, you can see the pads are there. That is a boundary. Okay, some pin muxing block is there. These are the pin muxing block. And some DFT instruments are there which can test any block, okay, using a signal routing and some hard IP and soft IP. So, and some analog devices, some digital device, some mixed signal blocks, and some security based block. So this is actually the top view of us of any IC. Now, what is soft IC? So soft IC means this is the intellectual property of any means hardware, because they have to put a software or some small kernel part in the IC. So that is the intellectual part, and that is a coded form. Actually, is a coded form. So this code may be in Verilog, VHDL, or system Verilog. Mostly industry are using system Verilog to make a soft IP, and it is an intellectual type. Means every company has taken a uh, copyright for soft IP. We cannot change all these soft IP. It is very rigid. And in hardware also there is pre-designed, because every you can see the what is the standard cell libraries are there. Okay. And that is familiarize the hardware components, what is the feature of this hardware components or block. Means we can do any part like synthesis, place and route based on the hardware IP. So hardware IP is also very rigid. Means that is also as compared to soft IP. Soft IP is not very rigid, but hardware IP is more rigid. So many standard libraries are there, which is in every EDA playground tool. So okay, so now if we see the power consumption is the important factor for any design, because here if we concentrate on this factor, we can control the battery power, and then of course the we can run the device for a long time. Okay, so many stages are there to control the power, like algorithms level, compiler level, architecture level, circuit level, and silicon level. Of course, all the stages is very difficult to control the power, but it is required actually. Otherwise, if the power consumption is more, the battery drain very fast, and the computing device needs more time, and that is not good, because now the device is more compact and consuming a low power. and that is a need of a customer. So if we say power, the power is computed by this formula alpha F CVDD square. Okay, alpha is activation factor. Okay, activation factor means how many times the switching take place from 0 to 1 or 1 to 0. Okay, and F is the frequency and C is the load capacitor and this is the supply voltage. So if we if you have a fast switching means like every time period if you are switching the logic, that means the device consume the activation factor will be high, because activation factor is computed by 0 to 1 or P1 to 0. Suppose that if you take AND gate, okay, this is like AND gate, and we know the true table of AND gate. This is 0, 0, 0, 1. So if we see the 0 means there is a 3 possibility here. So and the total probability means the outcomes is 4. And if we see the 1 only 1 times and the total outcomes is 1. So in this way we can calculate the activation factor. Activation factor is directly proportional to the power. So if the device in the means stable state means there is no dynamic power. Okay. So if the dynamic power is less, of course the total power is decided by static plus dynamic. Okay. So if there is a less switching or if there is less switching in the device, the dynamic power reduces. Another factor is the frequency. Means we are using a frequency and it is very high clock frequency because we need to perform multiple computations. So that is also consumer power. And another thing is that supply voltage is always less. That means the device consumes less power. So if we go to the energy computation part, this is the formula and we can see per cycle energy consumption, because energy is the important factor. So that to be minimized. Now I'm going to discuss the how the industry is manufacturing the IC. What are the important steps for the designing process? So first thing, you just look here the requirement. So suppose that any requirement for mobile manufacturing. So in manufacturing, what is the requirement of customer? We have to collect this requirement from the customer. So customer needs compact device and fast computing device. So the PPE factor, PPE is the power performance area factor and the cost. So these requirement we have to collect from the customer. And then we go to the higher level planning. So of course here in the higher level engineer, high level person like CEO of a company or the top leaders, they decide the planning process. Means how we go for the higher level design means they will plan like time schedule. They have to set the time. Means in this time period the whole the product manufacturing to be complete, and what are the requirement of resource, what are the software requirement, and what is the storage requirement and database. So that is decided by the higher level uh, manager. And then we come to the architecture. So architecture means it is a top level block. We cannot see inside the smaller block. First we have to decide the architecture. Means how many blocks are there and how many sub blocks are there. Because if you go to the synthesis part, we have to compute the output. So how many blocks are required for computing the signals? Okay, so here we can see we can also decide the technology node, which technology node we have to set for the architecture, or means architecture level means 45 nanometer, 65 nanometer, or industry is also going to 2 nanometer, like Apple processor there, Snapdragon software is there, and Intel is also launching a chip which is also very low technology node. So if the architecture level block is complete, then we go to logical level. So in logical level, we have to write a test, we have to write a netlist, okay, in terms of Verilog or system Verilog. Well, system Verilog is more preferable in the industry. So many of the EDA tools are there, like Synopsys, Spyglass is there for DRC checking, design rule checking, and low power checking, like Synopsys have a this bundle VCLP. So in the logic synthesis, we have to satisfy the power requirement or the DRC check. We have to satisfy, and if it is satisfied, we go to functional verifications. So in functional verifications, we are using a library cells, which is a standard library cells, which is provided by the EDA vendors, and we have to do the power computations, power calculations, delay calculations, and the area calculations. Okay, so if this factor is satisfied, then we have to deliver RTL. We have to deliver, and then this RTL we go to DFT. So DFT is again come to the two stage. One is normal DFT, another is in synthesis part. So now in normal DFT, many of the latest technology is there, like boundary scan method, okay, memory based, okay. So EDT is there, embedded deterministic test. So these are the actually modern way of testing of IC, because in that stage, if we short out the fault, then our cost is reduced, because if you go directly to the manufacturing, it is very costly, and at that time if any defects are there, that means whole manufacturing cost is waste. So in every stage we have to do the DFT, means design for test. If the testing is complete, then we have to pass the other stage. So this DFT is inserted in the RTL design, because this DFT code to include in the RTL. Okay, so that code is looking the simulations or fault simulations, fault coverage, test pattern generations. So according to the test pattern, we have to check the fault, we have to check the coverage, and how much percentage of coverage. If it is more than 90, then it is good. Every industry is looking more than 90% fault coverage. And if it is pass, then we go to like other checking, like VCLP checking. Okay, that is also a DFT functionality checking. Okay, so if this is part, we go to the RTL netlist, because RTL netlist is included the DFT, and if it is passed, we have to find out errors or some warning message. Okay, some DRC message, design rule check, warning message, everything. And if it is complete or it is passed, then we have to generate the first compiled report. Okay, so if this compiled report go to the other engineers, they will check again DRC, again by scan insertion method, many like boundary scan, to check the pins signal is going to properly or not. Of course, it is inserted the netlist, and if it is passed, then we have to generate the second compile report. And in the second compile report, there is a many of the important parameters also here, like power, delay, area factor. So if that is satisfied, if it is satisfied by the design engineer, then we have to again map this netlist to the coverage, fault coverage, how much fault coverage are there for this design. So we have many methods like ATPG, automatic test pattern generation method, using EDA playground, and then we check the fault coverage. And if by using the pattern simulation, if it is verified, then we go to the backend design. Backend design is showing the physical level, means it is a manufacturing part. So we have to do many things in the physical design, like partition, floor planning, placement, routing, and if it is proper, then the cost also reduce. Okay, so again in the physical verification, we have to do many sign-off process, which is available in the FDA tools like DRC, LVS, electrical rule check, layout versus schematic check, design rule check. And if it is satisfied, we have to go to this test, that is process voltage temperature check. Okay, PVT or all these things. And if it is satisfied, we have to again go the timing analysis. And so, because this is a manufacturing side, if it is satisfied, the timing simulation is satisfied, then we have to see the product is high quality. Okay, so we go to the simulations, verifications again, and using the pattern simulations. That is verified by the functional design, because the pattern simulation must be satisfied with functional design of a particular system. If it is satisfied, then we have to check the wafer is properly working or not, IC testing, hole testing. So many of the instruments are there because now in this stage the IC is totally packed. Okay, so we cannot see inside the architecture, we cannot see the sub blocks, and we cannot see the individual circuit, or we cannot go the circuit level also. So this is a high level testing. This is it is a manufacturing testing, because this is the final product. And if it is satisfied, this post layout will go to the fabrication. Means here we have to GDS2 file we have to transfer to the fab industry. So fab industry is doing the packaging and testing again. So of course, first we have to test this GDS2 file, and then we start the packaging. Again, after the packaging, we do the post silicon testing, and if it is satisfied, we have to take a feedback from the design engineers, and if it is satisfied, then the product is going to be launched. Now, the DFT part is more important. You can see in the many stages DFT involved. Because if any stage fails, then immediately we have to stop the manufacturing. So in DFT, now it is present time, it is more simple, because in DFT many techniques are there like BSD, boundary scan design method. So memory this technique, memory building self-testing. Okay, so in boundary scan is more popular. So many of the protocols are there. Okay, I need to tell you what are the protocols we are using in the boundary scan. Like 1149.1, this protocol is used for digital signal testing. Okay, and 1149.6 is used for analog tag testing, and 1149.7 is used for mixed signal type of testing. And if any high speed IC means high frequency clock, so high computation task, then this is the protocol for boundary scan. So these are the standard protocols. We just put our circuit in this architecture, and using the boundary, the signal is propagate, and then we can test our chip is very easily. So this DFT, most of the DFT industry follow the JTAG standard. So JTAG is a joint action test group protocols we have to follow for any kind of testing. Okay, so boundary scan designing also come in the JTAG. So there are many stages in the testing process you can see here, and many of the design engineer is many of the engineer is looking the different parts. So of course, if the chip is manufactured, and we have to again test this chip in terms of high temperature, in terms of low temperature, or extremely high frequency, or extremely low frequency. And if it is satisfied according to the requirement which is set by the top level manager like CEO or something higher level person, then the chip is going to be launched in the market. So that is very tough task actually. So you can see this is the instrument used for the DFT. Means in this instrument we can put our IC or our means system in this panel, and this test equipment automatically generates a test pattern using some algorithms, and the correct responses are also stored uh, in this what is because actually this is a simulator in this software. This is instrument have a simulator. So the correct response is matched to the actual response by this comparator block, and if it is match, the IC is pass or means good, or it is bad if it is not good. So if it is pass, then we have to means forward this information to the higher level. The manufacturing process is complete. Okay, so many of the testings are there actually. I just mentioned here. So that is a long means long work, means long task. It is a very big task. Okay, so I am going to tell you how many vendors are there, because these are the three main vendors, which is looking all the different stages. Like in the DFT, Mentor have a decent, and Synopsys has a Tetramax, and Cadence has a modest uh, tool list. We can do the DFT part. But in the physical design, the Cadence is more popular, because in our tool, we can do the physical design by this Cadence tool. And in the timing analysis, the Synopsys bundle is more effective, like prime time is more popular. And in the synthesis, Genus R is very good thing, means good EDA bundle. And RTL checking, the spyglass for Synopsys. And for yield things, and for yield means how many good chips are fabricated out of total chips. Means if any 100 chips are produced and 2 is faulty, that means 98 is the correct or good chip. So the yield factor must be high. Because if any faulty chip, that means its manufacturing cost also waste. Okay, so companies not looking the faulty chip. They have to save our cost also in the manufacturing state. So yield must be high. Okay. So many other tools are also there, ORCID, but this is outdated actually. It is only for the education purpose, means like a normal project, but industry is not using. Industry is using the Virtuoso tool or patterns for doing the like design of any circuit. So in that slide, I just tell you how the industry is manufacturing the chip. What are the main steps? So first, I discuss the silicon material. We have to use the silicon material as a raw material, and then we make a slice. Okay. So if the slice is ready, we go for the wafer. Means blank wafer. We have to generate. So if the wafer is important part, because in that wafer we are going to make a patterns, and so if the wafer is ready, we have to go to some VLSI technology. Means we have to perform a many processing steps like N-well deposition, P-well deposition, lithography, CVD process. So all these VLSI technology steps we have to apply, and then we have to make a patterns in the wafer. So now if the wafer pattern is ready, then
Sir,
we have
your
to
screen
test the
is
wafer.
not visible. Excuse me, sir.
Okay, so now I just show you the wafer testing. Means if the wafer is tested, and we have to check the individual patterns. Okay, so because if any wafer is defective, we have to reject the material in that stage. Then we have to save the manufacturing cost. So we have to see the blocks, because many blocks are there in the wafer, because we have formed a pattern in using some of these steps. And if any block is die, we have to reject this thing. So that is a dicer testing. And if it is pass, if the blocks is pass, then we have to make a package. Okay. So what are the effective packages, effective dies that we have to carry? Means we have to carry that dices only, and remaining blocks to be rejected in the wafer. And we have to go to individual testing also. Every block individual testing is also required. And if it is faulty, we have to remove this wafer, and then we have to ship this IC to customers. Okay, so this is the main manufacturing process of any IC. And in that manufacturing process, many stages are there. I have already tell you all these things. And in the GDS file, we have a many, because GDS is the in part. Before that, many steps are there, like in the backend part or in front end part. In backend part, these are the very costly steps, but like floor planning, placement, routing. Okay, so what is a process step out? So process step out means the GDS file to be handed over to the manufacturing fab industry. So before GDS, what are the important steps? I just presented here you the article design, the synthesis part, place and route, layout verification, and if the GDS file is ready, then we have to forward this to fabrication industry. So that is the end product. Okay, so here after that manufacturing process start. So this is the binary file format. We just see the blocks position what in the GDS2 file, and what are the materials are there in this place, and where is the signal routing stages. Everything is available in the GDS2 file. So that is a tap out process, and many of the part cells, all these layers information here in terms of only text message. This is only the text message type GDS file. So the founder industry will work if the GDS file is ready. They will use the manufacturing process. Okay, so in the GDS2 file, that means for layout viewing, many of the tools are there, like key layout, and verifications is there for exporting and is catalyst for layout notes there. Okay, so these are the tools that we use in the GDS2 file. And now in the RTL to structural level, many of the stages are there. So, but I'm going to present only the main modules or main blocks. One is the translator. Means high level codes are there. We have some netlist in terms of Verilog or VHDL or system Verilog. And then we have to apply the technology node. We have to apply the technology node. And then we have to optimize these three units. Okay, by the EDF background tool. And then we go for DFT. And DFT is looking for fault coverage. So in the synthesis, the genus bundle is more popular. That is for Cadence, and most of the industry is using the Cadence bundle for synthesis tool. Now I am going to discuss you if you are forward the GDS file to Foundry. It is not single step. It is around 12 steps. Okay, because if you are thinking GDS to the fab industry is not, it's not a normal task. It's a very big task. So first we have to prepare a rough draft, means the design data sheet. Okay, so if this data sheet is ready, we have to check the errors, and job docs are there, which can provide the information about the errors or docs. And then we have to contact the foundry. If it is third stage, if it is satisfied. Okay, if it is satisfied, then we have to forward contact to the foundry, and then we have to submit all the files. And again, we provide the files like GDS2 files. Then these files go to the design kit. Okay, so design kit again review the
Now it is visible, sir. You can continue, sir, please.
okay, sir. So here I have discussed about how you transfer the GDS file to Foundry. What are the steps are there? So 12 steps are there. We have to complete this 12 step. Then the GDS2 file transfer to Foundry. Okay. So next step. So now it is okay.
Sir.
Okay, so in that case, I am discussing now the present scenario is more tough because now IC is more complex, more components are there. So the testing of IC is more tough. But now the DFT is more mature. Means if we see the many JTAG standards are there, like IEEE 114 9.6. Okay, many analog digital pads are there. We can use these pads to make a DFT more easy. So the test planning. So all the chips means we have to physically verify it. If it is verified based on the patterns, okay, then we have to check this response. It is on actual response or not. In that case, suppose that this is some kind of circuits. So we have to apply some patterns, and this is the output pattern. So output pattern is already stored in the database. Suppose that this is IC and this pattern is already stored in the database. And if you apply some patterns, this output pattern is matched to the stored database. So it is a correct response. And this is the test response. And if the output pattern is matched with the stored database, it's verified by the computer. If it is matched, then the test result pass. And this is a normal testing actually. So what kind of test bench we have to generate in DFT? Okay, if we are using some normal circuits, and how we can import a test bench. Okay, now this is more. Okay, please let me know my screen visible.
Yes, sir.
Okay, so
Okay, so 5 minutes, within 5 minutes, you have to complete your presentation, sir, please.
Okay, sir. So in that slide, I am discuss about the DFT style, how we have to write DFT test bench. Means we have to use for loop, and this loop will go to the all the input combinations, and we have to apply the if conditions. If the input pattern is matched to the output, then we have to pass the IC. Okay. So this is about the look of DFT style, and this is all about result and simulation results. And now various methodology is there for testing, and one methodology is the boundary scan.
So thank you, sir, for your presentation. Now I invite Dr. N. Tamil Selvan, HOD of Mechanical Engineering, to propose the vote of thanks for this session. Please, sir. Sir, do you want to tell anything? Please, you have to conclude.
Okay, sir. Just 1 minute. I need to conclude. So in my presentation, I discussed about what is the current trends in the VLSI and what is the DFT, what are the available technique of DFT. I discussed about 114 9.1 architecture, and I discussed the DFT method, how to write a test bench, and how the industry is manufacturing the IC, what are the process flow, and how this GDS file to be.
It's my immense pleasure to introduce a vote of thanks for the technical session. Almost I extend our sincere gratitude our esteemed expert Dr. Neeraj Kumar for his enlightening the device level innovations and semiconductor for AI and IoT. Sir, please your depth presentation and research perspectives have truly inspired our faculty members and participants to explore further in this emerging domain. Sir, really I'm very happy. We have received a lot of information from this session. Once again, I thank you for giving this opportunity our management.
We come to the close of day 1 of our ATAL FDP on semiconductor for smart systems, applications in IoT, AI and next generation device. A big thank you to all our resource persons, dignitaries, faculty members, enthusiastic participants for making this day truly enriching. We look forward to seeing you all tomorrow for another exciting day of learning. Wishing you all a pleasant evening. Thank you.